I believe we finished this problem, these two problems here. Yes, 2, 4, 6, E, F, G, H.
Oh, yeah, but I didn't get all of these now.
Okay. We ran out of time right on this one. So we can look back at this. So to start with for the subsets, we had each of the individual subsets, E, F, G, and H. Then we went through the sets of 2. We listed EF, EG, EH. Those are the 3 pairs we would have with E in a set of 2. And the way that I do it, I always start with the first, whatever the first one in the set, and combine it in sets of 2 with the rest. Once we get that, we have all of E, we can move from E to F, which would give us FG and FH. There's no more that we can combine with F, so we move to G, H, and that's immediately done. So we good with all the sets of 1 and sets of 2? Because now we can move to sets of 3. E, F, G. Might as well start with the first 3 elements. Now for me, personally, when I look at this and do this, I move whatever the third term in that set is. So G, we can leave the first 2 the same, so we could have E, F, H. And if there was one after H, we could go E, F, K, E, F, and just keep changing that last one as far as we can. But really, we can only change it once, E, F, H. Now at this point here, since we can't move any farther, can change the third term, or third element. Well, I can go E, change F to G, and start again. So E, G, H, then E, G, and then do the same thing we did with the first one, where we're switching the H to any of the previous ones. But really, we just had E, G, H. Now at this point here, we can change G to the next one, but H, there's nothing after H. Really, we've done everything we can with E. So now we can move it to F. So for our 3 with F, it'd be FGH. And we're kind of stuck because there's nothing that we can change, alternate, or switch in for those. Do we have any other subsets? E, F, G, H. We have the whole thing. 15 of them. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 subsets. The fact that the previous one, when we had 3, had, I think it was 7, 6, 7 of them. So 3 elements had 7 subsets. We add 1 more, 4 elements have 15. If we added again, if we went to 5 elements, it would have 32 subsets. They increase dramatically. I think it's going to be something 2 to the n. Yeah, it's not 2n plus 1. It's probably 2 to the n plus 1. Or 2 to the n minus 1. One of the 2. Because 2 to the 5th, 2, 16, 32, 2, 2, 8, or 2, 4, 8, 16, 32. Yeah. There is an equation for it, but yeah. I'd have to look it up. Questions on these here? That's anything we've done so far. Now, the next thing we're jumping into is bounded and unbounded intervals. Now, what makes something a bounded interval is it has 2 endpoints. Now, we also have unbounded. Unbounded only has one endpoint. Now, there are four main types of bounded intervals. Let A and B be real numbers such that A is less than B. Then A and B are the endpoints of four different bounded intervals on the real number line. That is a lot of words. Let's break it down. Now, the first sentence, let A and B be two real numbers. That's just saying A and B can have any value. As long as it's a real number, we can set that value to it. And whenever we pick A to B, B has to be bigger, no matter what it is. So A could be negative 100. B could be negative 99, or it could be any other number bigger than it. It just has to be bigger. That's all that first sentence says. A and B are real numbers. A is smaller than B. That's all that says. And if we have this, we are able to define every possible bounded system, interval, inequality we could actually ever have. That's why we have this. That's why that's nice, is because just by setting that statement, I can set up every possible bounded interval with that information. Because the first one we can have is this top one here. As an inequality, it tells us A is less than or equal to X is less than or equal to B, whatever A and B are. As an interval, we use brackets, because if it's included, it's a bracket. Bracket A comma B bracket. If it's included, we have a bracket. If it's not included, we have parentheses for intervals. Graphically, it looks like that there. Or neither endpoint is included. So we have A is less than X is less than B. So parentheses A comma B parentheses. So the two first intervals that we have kind of as an inequality or interval notation is both included or not. So if they're both included, we have two brackets. If they're not included, we have two parentheses. The other two options. One's included, one's not. A is less than or equal to X is less than B. A is included, B is not. Or A is less than X is less than or equal to B. So A is not included, but B is. So for any bounded interval, it's going to be one of these four. The only thing that changes is based off of the given equation and the numbers. It's going to be one of these four, just the numbers are going to make it different for a given A and B. Questions on this here? Yes, sir.
What the brackets and parentheses meant.
So brackets in interval notation tell us that that point is included. It is equal to it. Parentheses says that it's not. We're going to get all the way up close to it, but not actually equal that number or that given value. Good question. Any other questions? So we good with bounded intervals? Or at least so far, we're mainly just talking in general sense. Now the other type that we have are unbounded intervals. Unbounded intervals only have one endpoint, and they continue indefinitely in one direction or the other. Let A be real number. Let A be a real number. So A is just any number. Each interval on the real number line shown below is called unbounded. So we just have one endpoint, and it's going to continue to the left or to the right of that point, depending on what inequality we have. So for the first inequality, we're saying that X is greater than or equal to A. So whatever A is, we're saying that X is bigger than it or equal to it. So X could be that value, or it could be bigger. And for our interval, we would have our bracket A, and the other side is going to be, the other endpoint, quote unquote, is going to be infinity. Because if it's bigger than it, it's going to start at whatever that value of A is and go to positive infinity because we're saying that it's bigger than it, it's greater than it. Now, if it's not equal to it, if x is just greater than a, we would have a similar interval notation, but instead of having a bracket, we're going to have a parenthesis. Because bracket says that it's equal to that value of a, parenthesis says it's not. It just has to be bigger than it. We also have the other direction, that it's less than a. If it's going to be less than this point, that means we're going to negative infinity. Same setup, just depending on if a is included or not. If a is indeed included, it is equal to it, we have a bracket. If it's not included, it is a. Now I do include this one here because if we do have all real numbers, it is the whole number line. We can say it's negative infinity to infinity, all real numbers, everything's included. Questions on this here? All right. So we feel comfortable with everything we've done so far, just talking about bounded, unbounded intervals. Yes? And we know why we can never get to infinity. Yes? Because infinity is not a number. Infinity is a concept. Because infinity is really for us to understand that whatever it's taking the place of, it's massively big or massively small. And no matter how hard we try, we can never get there. And depending on the context, there are some infinities that are bigger than others. Other contexts, there's just not. It's just depending on how it's set up. Now, one way to kind of illustrate this, there is a thought experiment that's talking about the infinite hotel. Yep. The infinite hotel is a great way to illustrate why we can't get to infinity. So I will be the desk clerk, just for the sake and point, of the infinite hotel. The infinite hotel has an infinite number of rooms. Infinite number of rooms. Every room is full. So tonight, every room is full. There's someone in every single room. And as the desk clerk, I'm working that night. Someone comes in asking for a room. Being good at my job, I want to try to get him a room. Well, what room? They're all full, yes? So after thinking for a bit, I decide to do this. I call the person up in room 1 and ask them to move to room 2. The person in room 2, going to have them to move to room 3. The person in room 3 is going to move to room 4. 4 is going to move to room 5, 5 to 6, 6 to 7. Everybody's going to go down one room. Well, how many rooms are there? Infinite amount. So everybody's going to move one down. Everybody's going to have a room, but that means room number 1 is now empty. So I can move the new guest into room 1. We just fit one more into infinity. Again, we can't get there. But all this is saying that we're quote unquote one off if we stretch our definitions a little bit here or there and how we think of that. But let's take it a step further. Now, the infinite hotel has been pretty popular, pretty successful, and for whatever reason, they decided to build an infinite hotel next to it and called it Infinite Hotel B, renamed the first one Infinite Hotel A. I don't know why they didn't put it somewhere else. They put it right next door. We have 2 infinite hotels, and both of them are booked. Not an empty room in either hotel. In a tragic case of events, Hotel B burns to the ground. It is gone. Luckily for us, or luckily for everybody in the hotel, everybody makes it out safe and sound. But we need to find a room for everybody that was staying in Hotel B. So we need to fit an infinite number of people into infinite Hotel A. What we can do, I'm going to do something not quite the same. I'm going to ask the person in room 1 to move to room 2. So I'm going to have the person in room 1 move to room 2. Well, that's no different than what we did. We'd only have one room, right? However, I'm not going to have the person in room 2 move to room 3. We'll have them move to room 4. We're going to have the person in room 3 go to room 6. The person in room 4 is going to room 8. The person in room 5 is going to room 10. We're moving them to the next even number. How many even numbers are there? Infinite number. And by doing this,
Isn't that double, not the next even?
double, next even, either way. We have 1 is now open, 3, 5, 7, 9. All of the odd numbers are now open. Or really, we're just saying it's multiplied by 2. And there's an infinite number of odd numbers. So we can move everybody from Hotel B into Hotel A. This can get, there is videos of this here because we can get all the way up to 7, 8, 9 different infinite hotels merged into one. The math gets a little funnier the more that get added, but it still works. And this is kind of just driving the point home that, again, we can't ever get to infinity, especially if we're talking about the numerical value of or thinking of it as a theoretical number. So, what we're going to do is rewrite these as interval or an interval notation. So our first one is -2 is less than or equal to x is less than or equal to 3. So there's different ways we can go about doing this. Because I think some of y'all have it down, or it looks like some of y'all have already written down what the interval notation is. If it helps to graph it, go on and graph it. Graph it on a number line. Or if you want to look back at the chart for bounded, because it has 2 endpoints, so it is bounded, yes? We can look at that there. I'm going to write this on the other page too, because this is the problem number we had, yes? Well, this corresponds to the top. It looks like the one on top, yes? But instead of A and B, we have what? -2 and 3. A is now what? -2. B is now 3, yes? And according to this setup, when A is less than or equal to X is less than or equal to B, the interval notation is bracket A comma B. So that means for us, we'd still have the bracket, but it's not going to be A anymore. It's going to be what? -2. And instead of B, we would have, so the interval notation would be bracket -2 comma 3 bracket. We said these 4 represent all bounded intervals. A is less than or equal to X is less than or equal to B is the general statement. We had -2 is less than or equal to X is less than or equal to 3. A is now -2, B is now 3. We just substitute in. Now, the other way you can do this, and I look at these here with intervals, especially bounded intervals have 2 endpoints. So the interval should have 2 endpoints. And its endpoints are the 2 ends, -2 and 3. Those are our 2 endpoints. Now we need to determine if they're included or not. Are they going to be equal to our x? -2 is less than or equal. So since it's equal, we would put a bracket. Then we would look at the 3. X is less than or equal to 3. So we would also have a bracket. If it had just said less than, it did not have the equal sign, we would put a parenthesis. That is it. Questions on this here? Question? All right. Let's look at B. X is greater than -1. Is this bounded or unbounded? Unbounded. So we have one endpoint and it continues indefinitely in one direction or the other. So that tells me a few things. Just from looking at this here, I have one endpoint. That means the other number that's going to be included for the interval notation has to be one of two things. Either infinity or negative infinity. Now, which one we choose it or have depends on which direction it's going. If it's getting bigger, it's going to be infinity. If it's getting smaller, it's going to be negative infinity. So are the numbers getting bigger or smaller? Bigger. So we're saying that x has to be greater than -1. We want numbers bigger than -1. So we know that it has to get bigger. So we know the other side has to be infinity. So a good question, why do we put the -1 first? So the reason we put -1 first is it's just like a number line. We want the smaller numbers on the left, bigger numbers on the right. It's almost like we're graphing it. Smaller numbers on the left, bigger numbers on the right. It's more, what it's really doing is we're following something called number theory. Number theory is a set of study in mathematics that defines how we write and notate everything. So number theory states that we normally do it left to right. It also, especially with writing stuff in order or an equation, alphabetical order by powers, whichever one has the biggest exponent first, and then alphabetical order. So A goes first, B, C, D. We have that there. That's also why ordered pairs are always in the form x comma y. Alphabetically, x comes first, y comes second. Especially ordered triplets, x, y, z. That is a good question. Any other questions? Now we need to put our parentheses in brackets. Is -1 included? As we look here, do we have an equal sign? This would be a parenthesis, because x is greater than -1. If it was greater than or equal, then we would include the bracket. What do we do with the infinity? Now, just like the first one, we could actually go to the unbounded interval. We know we have one endpoint, yes? Which of these four does it match up with? The second one, yes? X is greater than A. Well, what's our value of A? So we're going to replace that with the exact same thing. That's the nice thing with this, especially these tables. They are going to follow any and all bounded and unbounded. They always follow this method, this pattern. Questions on this here? C and D, they did not give us an inequality. They gave us a graph. Now, it feels like we can't use that chart, but luckily for y'all, I did include the graphical representation of the chart too, so we could use those there. As we look at C, how many endpoints do we have? 2. And they are -3 and 4. So this is bounded between -3 and 4. So if we wanted to look at the chart for bounded intervals, we can look at these here. And as we see here, we do have a closed circle on the left, open circle on the right. Well, that matches up to the third one, yes? Now, A on this example has been replaced with what? -3, and B has been replaced with 4? I don't know why I was thinking 2. 4. Now we just replace A and B, yes? So bracket A comma B would be bracket -3, 4. Inequality, if we wanted to, it didn't ask. We have what? -3 is less than or equal to x is less than 4. Well, the way I look at this a lot of times is we see the two endpoints, -3 and 4. We're going to put a comma between them because we're saying it starts at -3, it ends at 4. Now we're determining if one or both are included. As we look at -3, we see, is that circle filled in or not? Since it is, we would put a bracket. Then we would look at the 4 and see if it's filled in or not. It's not, so we would put a parentheses. So the interval would be bracket -3, comma 4. Questions on this here? We ready for the next one? D. We have the graph of this here. Is it bounded or unbounded? Unbounded. It runs all the way off the number line, yes? And we have one endpoint at what? 3. So we can go back to it. We'll do that here in a second. To the unbounded interval chart. And we can match it up and go from there. If we didn't want to, I know 3 is going to be one of the endpoints. So we know it's going to be listed, yes? So that means the other endpoint, quote unquote endpoint, the direction we're going is going to have to be infinity or negative infinity. Which one are we going to? Negative infinity, because we're going smaller, yes? And since we're going smaller, it has to be on the left. Because negative infinity is definitely smaller than 3. So we would have negative infinity, comma 3. Would negative infinity have a parentheses or a bracket? Parentheses. Would it ever have a bracket? No. Infinity and negative infinity will always have a parentheses. The 3, is it included? So it would be a bracket. Interval notation. Questions on this here? Y'all remember doing this Algebra 1, middle school some? It should have been, y'all have seen this a few times at this point. We ready for the next piece? Yes. It should look something like this here. Now before we get there, there's a reason we have this. You do not need to write this, don't write this. So if we wanted to write in set notation the set of all real numbers greater than or equal to 0. Because up to this point, we've been able to write everything in set notation. Because as we did this yesterday, if I wanted to write this set, we'd have a brace. And then the first number we could put is 0, yes? What would be the next real number? Well, we could have 1. But would 0.1 be a number? Yeah, okay. What about 0.876253221? Yeah. How about 0.37986? Yeah. How about 1/2? 1/3? 1/4? 1/5? 1/6? 1/7? 1/8? 1/9? Well, I can just put 1 over every natural number, yes? How about 2/3? 2/4? Well, 2/4 is 1/2, but that's fine. 2/5, 2/6, 2/7. We can do 3/4, 3/5, 3/6, 3/7, 3/8, 4/5, 5. Is there any reasonable way to write all this? If you notice, we actually haven't even gotten to 1 yet. We're just covering numbers between 0 and 1. Yep. So realistically, there is no way for us to write all the set of all real numbers greater than or equal to 0. And if you notice, we have kind of sort of set up a pattern, especially for these fractions. We're good with those. But there's a good chance some of these irrational numbers that are between 0 and 1 aren't going to be covered. So there's no way to actually set a pattern that works for this. So we need a way to actually describe these sets of numbers, this group, without a pattern or being able to write them all out. That's where we get set builder notation. This gives us a way to describe a set or a group of numbers that is not easily writable or building a set pattern. Now, I do it this way. I give us these numbers, or these setup, so that we don't have something necessarily that we're directly connecting it to. These 3 pieces, it's always braces, triangle, bar, circle. Now, the triangle, what we put in place of the triangle is what is our group? What number group are we talking about? Are we talking about real numbers, rational numbers, irrational, whole, natural? What is our number group that we're talking about? What types of numbers are we talking about? This is what goes there. Now, for the most part, it's going to be brace X bar. If it's brace X and then the bar, we're talking about the set of all real numbers. If we're talking about real numbers, we don't have to specify, it's understood. Now, the circle is going to be our description, what we define the numbers are. This is going to be most likely an interval. X is greater than 4. X is less than -2. X is even. X is odd. We can give it some description so we know what type of numbers we're talking about. Are you ready for the bar in the middle? Such that. That's literally all it means. It is actually, that bar is understood to be such that. So we could say the set of all real numbers such that X is greater than 4. So we know that we're talking about all real numbers greater than 4. We actually have a description of it. So the triangle is going to be what type of numbers are we talking about? Such that it satisfies this description. So how does that look? Well, we have some examples here. So the first one, again, it looks like we've got some complicated mess up here. Brace X bar, X is less than A. So this first part here, the brace X bar, we're saying that the set of all real numbers X, such that X is less than A. So we're saying whatever A is, all the numbers less than it is the group that we're talking about, the set of numbers we're talking about. Do we know what A is? No. Graphically, if we put this here, somewhere on the number line we do have A, yes? We put a circle. Is A included? Whatever it is. No, because it does not say less than or equal, it's just less than, yes? And it's going to be all the numbers to the left. So graphically, that's all that said. All the real numbers less than A. That's it. It just gives us a way to describe this set. All the numbers less than A. Well, that seems kind of tedious. Why would we do this? Yes? I mean, the other way to do this is we have the set of all real numbers less than x. So we took that whole sentence and rewrote it into that. I think that's a little bit nicer to say the same exact thing, yes? And for the most part, it doesn't seem like it's nicer until we actually see side by side what we're saying and what we're actually writing. The next one, I find it kind of funny. Because brace x bar is telling us what? The set of all real numbers x, yes? Such that, what? X is not equal to 3. So if I were to graph this, we'd have a point at 3, yes? Would it be open or closed? Open, because it can't be equal to 3, yes? What could it be? 4, 5, pi, 2, 1. It can be anything, it just cannot be 3. So what can we do? Could we shade to the right? Yeah, could we shade to the left? It's actually the entire number line. It's just not 3. I don't know what 3 did, but apparently he's out. Yep. So what are we thinking of set builder so far? It feels like it should be more than this, but that's all this is. We're describing the set of numbers. We're saying which numbers we're talking about and giving it a description. Like if we look at the next one, brace x bar, the set of all real numbers x. We're talking about any number on the number line, such that -4 is less than x is less than or equal to 6. We're saying out of all the numbers on the number line, it has to be between -4 and 6. It's got to be between these two, so we know it's going to be shaded here. Is -4 included? No. Is 6 included? Especially if we're asked to just graph it, we have this here. Now, especially the set of all real numbers, it's like, okay, cool, all the numbers on the number line, we'll just graph it. And we get this here. Yes, now the question is, what is that E? That E stands for element. X is an element of, we can put something in that blank, such that X is greater than or equal to 9. Now, you don't need to write this, because we could say, we could put the R with 2 lines. This is redundant. Because you remember what number set that matches with? As y'all can look, it's on page 1. Real numbers. So we're saying X is an element of the real numbers. Why is that redundant? Because if I didn't put that at all, brace X bar is X is a real number, the set of all real numbers. I don't need that. Because if we're talking about real numbers, we're just going brace X bar. We put element if we are not talking about real numbers. So we're not talking about complex numbers. What we're saying is that we could put, say, our Z with a line, which would be integers. X is an element of the integers such that X is greater than or equal to -9. So we're talking about all the integers greater than -9. Graphically, that's not as nice to graph because our integers are positive and negative counting numbers, which means we would have -9, -8, -7. We would just have all the points. We don't have anything in between. Especially with graphing, or if we're graphing something or taking a graph to set builder notation, we're talking about the real numbers. We're talking about everything in between that whole number line, whatever's included. Graphing the last one's also kind of a trick too, because we're just graphing points. We're graphing just the even numbers, because it says the set of all real numbers x such that x is even. So it's just going to be a whole lot of points. Does this kind of make sense? This is not the only way to write this, especially if we go by the textbook. Textbooks are just a resource. I disagree with them sometimes. The way that the textbook says we can write this, and it's not wrong, I just think it's a little more tedious. We can go brace x bar. We can say the set of all real numbers x such that we want x to be what? X is an integer and x is greater than or equal to that says the exact same thing. You know, you're right. We can definitely use x as an element of the integers and x is greater than or equal to 9. It's saying the exact same thing. But if we're doing that, we might as well throw x as an element of the integers on the other side. Then yes, we can actually simplify that further. You don't have to keep writing these if you don't want to. X is an element of the integers and that thing that looks like a tent or the caret key for doing exponents. In set builder or in proofs, that is and. That's a way that we can write and. Flip it upside down, it'd be a little v, that's or. So many ways to write this, yes? Above and beyond, you will never use it. For all x in the integers, x is greater than or equal to -9. That is the exact same thing. It's just not in straight set builder notation. When you go to proofs, if you do proofs, upper level proofs, that is how they write everything with the for all, the upside down A, and a backwards E, capital E for exists. There is a number. But above and beyond. Questions on this here? We will finish this tomorrow.